All right, and we're back for the second hour here on Monday, July 6th, finishing up actually chapter 19, carboxylic acids, test one due tonight. Don't wait until midnight to get it in, get it out, get it in well before. It shouldn't take more than a couple hours, 40 multiple choice questions. Make sure you start it early enough in the day. And then tomorrow is when homework 4 will be due. Now, I'd like to show you here on the overhead, so can they see up there? Okay. Um, to what extent do carboxylic acids ionize in water? Okay. So here's your carboxylic acid. R would be a methyl group there for acetic acid. But I'm leaving it general enough to show you how mathematically we can do this and how the experiment actually works. Here's the general equilibrium. If you put this acid in water, to what extent does this really donate a proton to water to make hydronium ion and carboxylate? Here's the general Ka expression that I drew. Notice it doesn't include water because it's specific for acid ionization in water. So we keep water constant. You can measure this. There's different ways to measure this and know this number very accurately. You can measure it spectrometrically and see how much carboxylate versus neutral acid is in the solution. There are ways to detect both of those. And this is 1.8 times 10 to the minus 5 for acetic acid. Now, those are big numbers or super small numbers, log 10 values. We take minus of the log 10 of this number, and we get about 5, 4.7, 4.8, whatever. So that's minus log 10 of the pKa right there, okay? Well, we can rearrange this general equation here to this expression. This is called the Henderson-Hasselbalch equation. It looks intimidating, but all this is taking the log of both sides. See, log Ka, log hydronium ion, that's in the numerator. And then this ratio of carboxylate to neutral acid, the log of that ratio. We could break that out different ways, but the math holds out there, just taking the log of both sides. Then we recognize here's the negative of the negative log Ka. That's what? The pKa. There it is right there. And what's this? Log hydronium ion. That's right. The negative of that is the pH. Okay. So you see how these equations work there. And then we have the log 10 of the ratio of the acid. Now we had to flip it over. And you can flip it over and have the minus signs change, whatever. But that gives you the ratio of neutral to ionized, depending on what the Ka for that acid is and what pH the solution is. So in water, neutral water, that's pH 7, right? So there it is. And we know the pKa of acetic acid, it's right there. So we can solve for this ratio of acetic acid to acetate. So we bring the 7 over here, of course. That's negative now 2.3. And we take the inverse log of both sides, so this just becomes the ratio. Inverse log of negative 2.3 is 0.005. So what does that mean? It's only 5% neutral acetic acid, and it's over 95%, 0.5%, sorry, and it's 95.5% of acetate. So it's all ionized, you could say, right? Qualitatively, I like this depiction better. This really relates it to the structure that we're interested in. A lot of times, especially beginning students, just get used to plugging numbers into equations. That's not what we're doing here. We're looking at the structure here. This carboxylic acid, to what extent can it ionize? Well, its conjugate base is resonance stabilized. So yeah, it's a relatively weak acid. It's not as strong as HCl or sulfuric acid, but its pKa is 5, which is significant. It is a weak protic acid, which means based on the pH range here of 0 to 14, neutral being 7, we're on what? The acidic side of its, I'm sorry, if we're down here at the pKa, you see we're in the acidic range. But if we're to the right of this pKa, which is right here at 4.8, if we're to the right here, that's the acidic side of that pKa. So we'll mainly be forming acetate. We'll have enough base strength to pull that proton off. So anything above 5 here is acetate mainly. Anything below 5, more acidic, is what? Acetic acid, okay? A 0 pH means 1 molar hydronium ion. That's very strong acid concentrations. But at neutral water, you have low concentrations of both acid and base. But you have enough base to deprotonate there, and it's essentially all ionized, okay? Now, if this was a strong acid and we put in 1 mole of acetic acid, it would all go down to pH 0, like HCl and sulfuric acid do. But when you put in 1 mole of acetic acid here, it ionizes only to a partial extent there, okay? And what, if we're at 7, we're basic enough that we can ionize most of it, almost all of it. We still have a little bit of acid here, okay? And we still have enough hydronium ion concentration, which makes it still quite acidic. Anyway, so the percent ionization, you can use the Henderson-Hasselbalch or this qualitative scheme, putting the compound on the pH range, and we'll do that with some acetic acids later on, and amino acids. I'll do the applications later. I wanted to go to the board and do some more calculations of some different bases with acetic acid. So we figured this one out. Sodium hydroxide definitely going to the weaker acid here. The equilibrium for this reaction would be 10 to the 10 power. So sodium hydroxide, as soon as it sees acetic acid, will go all the way. So this is different than talking about just putting it in water. Now we've got one equivalent of strong base, right? Sodium hydroxide. That creates the weaker acid water in this case. The stronger acid is actually acetic acid. What about sodium ethoxide? Well, we get the same product here, except we get this. We get the neutral alcohol as our conjugate acid. And what's the pK of that? Well, it's 18. So it's 18 minus 5. So that's even better, right? This would be 10 to the 13th power, okay? What about sodium phenolate? If we do that, well, then we get the phenol product here. And that will give us our phenol, and the pK of that is known too. It's 10, okay? Which means what? It's a stronger acid than water or phenol there, which means it's a little bit weaker base, but we can do the calculation here, 10 minus 5, yeah, 10 to the 5th, okay? So it's still favorable there. We might want to figure out, you see, why phenolate is a weaker base. It's a stronger acid, weaker base than that. We can compare that to water there and see why that is. In phenol, we have this extra resonance effect, right? Okay, so that can be stabilizing there. What about ammonium? So if we have ammonia as a base, and it has a lone pair here, it's neutral, but if it reacts with acetic acid here, the byproduct will be ammonium cation, and the pKa of that is what? 9. So the equilibrium constant for this reaction of acetic acid with ammonia will be what? 9 minus 5, or 10 to the 4th. Okay, so not as favored, but certainly very high equilibrium constant of 1,000, right? And let's see, here's a primary amine. We've got a propyl group on the amine. Still have a lone pair there, and our byproduct will be this propyl ammonium. Well, I meant propyl. Sorry. And plus charge, and it's also about 9. So it'll also be about 10 to the 4th power there. So yeah, let's compare that. We've got pKa's here of this guy, pKa of ethanol, 18, pKa of phenol, 10. We did a comparison of these in 351, and there are some other discussions in different places. So which one is the strongest acid? Well, it's definitely the acetic acid. Why? Because when it ionizes, it has the resonance stabilized carboxylate, right? So yeah, it has the lowest number here. The lower the number pKa-wise means the stronger acid. What about this one? Well, that has just O minus, localized Rana, no resonance effect there. So it's harder to pull that proton off, so it's what? A weaker acid, okay? Which also means it's a stronger base compared to acetate, okay? So there's different ways of looking at this. How about phenol and then phenolate? Why is that pKa 10 here? Well, it's because it does have resonance effects. We can push the negative charge here, here, and here. And you might say, well, that's 3 more resonance structures. Carboxylate only has the 2. Why is this not as strong an acid as acetic acid? Well, it's because these resonance structures here are on carbon, which is not as electronegative as oxygen. Here in carboxylate, you have 2 negative charges on very electronegative oxygen. So that resonance effect is actually more important than this, where you have the negative charges actually on carbon. And here you don't have any resonance charges, right? So this is our weakest acid. Here's our next acid, and here's our most potent acid comparing these. And these are all just hydroxyl groups, right? But they're very different range, 5 all the way up to 18. So that's another way to look at it and keep track of it there. All right, let's look at some more pKa values here on benzoic acid. And there's some subtle differences here that your book points out. Benzoic acid itself is, yeah, a little bit more acidic than acetic acid, but not by much. So reacting this with some sort of a base, yeah, we can pull that off. The pKa here is 4.2, okay? Remember we said acetic acid was what, 4.7, 4.8, depending on who you believe in the literature. I think your book says 4.8. But this would be a little more acidic, right? Because it's a little bit lower number. And you could say, well, this is conjugated through here, but you can't really push electrons and have the negative charge in here. This is just, the pi system is conjugated this way, and the negative charge is still localized out here on the carboxylate. But because you have this group here, it does make it a little more acidic. But if you have a donor group on here, let's see this number here. I think I've got a couple on here. If you have this one, an alkyl one, if you have a toluene group here, a paramethyl benzoic acid, this is a donor group by what? Inductive donation or hyperconjugation. That's going to be pushing more electron density in here, and that's not going to help you stabilize this negative charge. In fact, it goes the other way, I think. Yeah, 4.4, it's a little less acidic. Now, that's a very subtle effect. Don't worry so much about that. But if you have a withdrawing group, let's see this nitro group, and remember nitro groups, NO2, always has a plus charge right on the nitrogen. So if we were to ionize that, para-nitrobenzoic acid, now you have a plus charge and this negative charge. And even though you can't push electrons through there, try it. You can't push these electrons through there. They only push up there. You can't push them through the ring. But because you have the negative charge here and the positive charge here, that's called a field effect. Okay? These field effects can actually stabilize a molecule as well. So if this is more stabilized relative to benzoic acid, what should be the pKa here? Yeah, it's a little bit lower. It should be, yeah, 3.5, the pKa. The lower the number, the more acidic, again, because of this field effect of the withdrawing group now, okay, as opposed to the donor group. And I think those are very subtle effects, okay? Let me show you an effect that's not so subtle. We already did this one, right? Phenol, pKa of what? 10, right? How about this? And we can make this trinitrophenol. It has a name, picric acid, common name, and yes, it is a detonation hazard, just like TNT. pKa of 10 here. What about the pKa here? Well, we need to look at the conjugate base. How stable is this conjugate base relative to that one? What do you guess? pKa lower now or higher than 10? Right, lower. And how much lower? Well, you can see now you can push electrons here all around the ring, and you get a negative charge right here next door to the positive charge. That's a good thing. And you can keep pushing these electrons down here, right? and get resonance stable. You can draw numerous resonance structures here for picric acid conjugate base. So the pKa here is 0.2 exclamation point. So that's, 10 orders of magnitude stabilization. And that's because of significant resonance effect here. Not so much with the benzoic acids, but that's probably enough there. Let's look at a couple other field effects. And I think we looked at these in 351 also. So pKa again of 4.8. And what if we have chloroacetic acid? How about well, let's just go right up to trichloro. I got a bunch of numbers here, but we don't need to do them all. How about, trifluoro. I like that one. And let's see, how about if we have the chain longer here? How many do I have there? Oh, 4. Okay, so relate all of these. These are our carboxylic acids, right? If we have one chloro here, what is that going to do to the conjugate base? Is it going to make it more stabilized? And yeah, because of this polar covalent bond with this electronegative atom out, partially positive end here is close to the negative charge there. It's another field effect, actually. You're not pushing electrons to stabilize here. But what does this do to the pKa here? Yeah, it's 2.8. It's actually significant, okay? And if you have 3 chloros on there, it's 0.9. Okay, you're bordering on the strong acid area, right? Which is below 0. How about this one? Now we have intervening methylenes here. So compared to this one, 2.8, what would you predict there? More acidic or less acidic? Yeah, less acidic, but it's still a little bit below 4.8, I think. Yeah, it's 4.5. Just a little bit, okay? So the field effect dissipates if you have a lot of carbons in between there. And what about this guy? Trifluoroacetic acid. What do you think there? 3 more electronegative groups in there. Yeah, so significantly more acidic, 0.2 pKa than 0.9. Well, it's kind of close to that one, but yeah. So TFA, or trifluoroacetic acid, much more acidic there. Oxalic acid. We could do this one. Let's see. The first one comes off actually at 1.2. And why is that? Well, when you take the first one off, you've got a field effect, right? You've got this partially positive carbon right here, okay? So yeah, that makes that first one more acidic. To take out the second one and make the oxalate dianion look like this. To take that second one off, that's 4.3. So that's comparable to acetic acid. But again, you have the field effect here. You have this partially positive carbon. Even though this is ionized still, it's not to the same extent. And like I said, here's the calcium salt of oxalate. That's kidney stones, okay? Should be aware of clinical applications of some of these things. All right, I think that's good. No, let me show you. Sorry, sulfates and phosphates real quick. So we know this one, paratoluene sulfonic acid. We know how to sulfonate toluene. And there it is there. The pKa of this is quite low, -3. So it's similar to sulfuric acid, you could say. We can convert this to the paratoluene sulfonyl chloride. And you've seen that reagent too. Where did we see that? We saw that in 351. This is tosyl chloride to make a tosylate, okay? So that kind of ties in there. But why? Take the proton off, very resonance stabilized, more resonance stabilized relative to acetic acid. And then we got phosphoric acids. Let's see, which one do I want to draw here? Oh, how about just this one? Oh. Phosphorus is the same row as nitrogen, so it has 5 valence electrons. It's a diprotic acid, and the pKa's here, I think I've got them. Where are they? Oh, the 2.1 is the first one, and 6.9. So yeah, the first one can come off and it's resonance stabilized, kind of like a carboxylic acid, right? But then the second one coming off is not nearly as acidic. And so we'll see different states in biology where you can have the biphosphate here, or you can have the full phosphate. And if you're around pH 7, which is physiological conditions, this one becomes the major one, okay? Because that pH 7 is what? A little bit on the basic side of both of these. Well, a little bit on that one, but certainly on that one. And so you can have the full phosphate projection there. All right. Yeah. Well, I've got to do a little bit more on the board. And then we'll go back to the overhead here to say we got to do the amino acids first. So sorry, I wanted to get to those applications quickly. Well, let's see. So alpha amino acids. And you've heard this term, I'm sure, in many different places. Alpha amino acid, what is it? Well, it's a carboxylic acid where at the 2 position, you have an amino group. Okay, so there are 2 amino carboxylic acids. This alpha position is numbering down the chain here, alpha, beta, gamma, delta. It's a common way of naming that. So the alpha amino acids, the ones that go into proteins, make peptide chains, make polyamides. We'll see how that relates later. Has carboxylic acid and the amine group here. Now, most of the amines in biology have this type of stereocenter. So the top priority is what? Nitrogen here. Okay, that'd be 1. Next priority is 2. Remember, nitrogen's to the right of carbon there in the periodic table. So nitrogen has priority over carbon. And then the other chain here usually doesn't have 2 oxygens on it. So that's number 2, and then 3 there. And so what's the sense of that rotation? Well, it's counterclockwise. So they're mainly S in nature, okay? They're often called L amino acids too. We'll have to see what that means. I shouldn't say all amino acids. Glycine is achiral, okay? Glycine, the R group, is another hydrogen. That's the simplest amino acid. And what about this one? Cysteine. You'll see that later on. That turns out to have an R stereocenter because there's a sulfur in the side chain, which has priority over the carbon here. So that actually rotates clockwise. But all the other amino acids, and there are 18 other ones, will all have the S stereocenter right there. Now, what about this L thing here? Well, if we put our eyeball right here and look down this middle carbon right there, look at the front of that, the view we'll have is this. Okay, so we have the amino group coming out over here. That's this part right here, and this, and then the carboxylic acid and the side chain here are right there. Okay, and what we see here is this is coming out at us, and that's coming out at you, and then you do the rotation again if you'd like there, and see it's still S. But the stereocenter here being over on the left side means that that's the L series, okay? The ones in nature are all the L series. There are some rare forms where we have the D amino acids. The D position is to the right, this last stereocenter, but we can assign that absolutely as S. The L versus D designations are kind of archaic, but they persist in the literature and in your book. The S and the R are absolute designations of the stereocenters. All right, let's look at the ionization just briefly of amino acids, and we'll relate this to the pH scale. So I already, went through the different ionization states that we can have here. So let's go from 14 down to 7 down to 0, okay? So 0 pH, this is what we're talking about here. Here, the concentration of hydronium ion is equal to 1 molar hydronium ion, super acidic. What does the concentration of hydronium equal at 14? Right, it's minus 14 molarity. And then we can look at the concentration of hydroxide as being 1 molar. Okay. Remember, it's always a function of the water equilibrium constant, the Kw, which is the two together here, where the concentration of hydronium and hydroxide always equals what? 10 to the 10 to the minus 14. So at 7, we have concentration of hydronium of minus 7 molarity, 10 to the minus 7. And here we have concentration of hydroxide of 10 to the minus 7. Okay, they're the same at 7. That's why we call that the neutral point there. All right, so we've got a carboxylic acid here, and we've got our ammonium group. Okay, and we've got a methyl group here. That's a generic one. That's actually alanine. One of the 18 other amino acids. And so what do we got here? Well, we've got the ability to grab a base and deprotonate there. The pKa of this is about 2.2. And why is that so much lower and more acidic than a normal carboxylic acid? It's because of the proximity to the electronegative nitrogen, okay? And then we also have the ammonium version here, which will have what? NH3 plus charge there. And the pKa of an ammonium cation is 9. So those are the two numbers to keep in mind there, 9 and 2.2 for the different groups. So let's go down here to a pH of 1. And if we have that there, the carboxylate will still be protonated and the amine will be protonated. Okay, if we're at pH 1. The pKa, of 2.2 here, we're on the acidic side of it, so that carboxylate stays protonated. Okay, then all the way from 2.2 up here to 9, those are the two pKa's now. pKa of 2.2 referring to that. That's what we need to worry about. Notice we're on the acidic side of this pKa, which is 9. So that will be ammonium cation, NH3 there, bonded to the carbon there. There's your 4 there. So this whole area here will be this. It'll be the ammonium carboxylate, or the zwitterion, as we call that. Okay. And that's the neutral form of that amino acid, anywhere from a pH of 2.2 up to 9. So this is the bottom part, referring to the aqueous solution, where we're at here. Because we're on the basic side of this pKa, we've ionized it, right? So anything in here is going to mainly have that. Now, when we get to 9, now we're increasing the basicity. We're increasing hydroxide concentration. And what do we get to here? Well, we'll have carboxylate still. And what do we have? We'll have the neutral amine. We've got enough base on the basic side of this pKa to take that proton off, so we'll have this. So what's our overall charge here? The basic side, -1. What's our charge here in the middle between the two pKa's? 0. Okay. And what about way down here on the acidic side? The overall charge is +1. Okay. So that's what we expect you to be able to do. For any given problem, you'll be given the pKa's here. This is lower or more acidic due to the field effect going to an amino acid, but you should be able to figure that out. One other thing here, the PI value. What does that mean? That's the isoelectric point. That's where you got the maximum amount of neutral, okay? Well, where is that going to be here? You've got one group that can become negative charge, one group that can become positively charged. So it will be this middle point averaging between these two that affect that neutral charge. So what would it be? 9 plus 2.2 divided by 2. And what does it turn out to be there for the neutral one there? 6 point something. Yeah, what is that? 11.2. Yeah, I don't know. It's in between the two. It's about 6. Okay. A lot of them are the isoelectric point will be around 6. But we'll have some other ones we'll look at in a later chapter where some of the side chains, some of these R groups can ionize, and that will change the pi value. All right, yeah, so work through those problems and be aware of those things. The only two pKa numbers I want you to memorize at this point are the carboxylic acid around 5 and the ammonium cations at 9, okay? If we have you do a problem on a quiz or a test, we'll give you the other value. All right, let's go back up here on the board and look at some of the applications of carboxylic acids. Yes, they're all over the place in biology and in medicine. There's a number of carboxylic acids that are therapeutic drugs. We have bufenac here and ibuprofen or Advil. Some of you have probably taken that. Of course, aspirin. A lot of you have taken that. And you've got a carboxylic acid. So that can ionize, right? Let's see, in the stomach, what's the pH? If you take this drug orally, what's your stomach pH? Yeah, it's around 2. That's because your stomach, upon digestion, if you've eaten something, the pH goes way down. There are specialized cells that release acid. And so these drugs will stay protonated at that point. Now, in order to pass into the bloodstream and be more soluble in water, and that's, of course, neutral pH, right? What's going to happen there? Well, if it becomes neutralized, they will become ionized. So aspirin, when it's absorbed into the bloodstream, will be deprotonated, okay? Because that pH now is well above the pKa value. So some important drug transport things there. How do these drugs work? These are non-steroidal anti-inflammatory agents. They're all related to aspirin, which is the first one based on a natural product, salicylic acid. Advil and naproxen, you'll see in a second, all inhibit this enzyme called COX, which is cyclooxygenase. There's 2 isoforms, COX-1 and COX-2. Aspirin's not very selective. It inhibits at 300 nanomolar COX-1 and COX-2 at 2.4 micromolar. You want these lower concentrations. Nanomolar concentration is 10 to the minus 9 molarity. It's very dilute concentration. Anything above that value, it can inhibit that enzyme. So why are we talking about this enzyme? Well, this is the enzyme that makes prostaglandins, which are also carboxylic acids, which mediates inflammation, pain, and fever in the body. So aspirin can lower pain and fever by inhibiting the enzyme that makes prostaglandin. Prostaglandin mediates that inflammation process. And I show here the structure of ibuprofen in red bound in the binding site of COX-1, and you'll see in a second how COX works. And here's the open binding site where the arachidonic acid leading to prostaglandin binds. So there's a lot of issues there, right? Structurally. Prostaglandins, here they are. They're from arachidonic acid. Upon injury in the body, this becomes hydrolyzed off one of the acyl triglycerides in the lipid bilayer membrane, in the barriers between cells. When it's exposed to oxygen upon injury there, oxygen from air can come in. And these COX proteins convert arachidonic acid into PGs, prostaglandins. And I show here the different pathways that these mediate. These are localized hormones within the body. They're not circulating hormones. They just do their activity locally, generally. But there's a whole host of these that mediate different things. Vasoconstriction, what's that referring to? Right, blood vessel constriction. So it tightens blood vessels and increases blood pressure. Then we have vasodilators down here, just changing the structure on the prostaglandin from this alcohol to a ketone here. You get the dilation or the relaxing of that. And they have different designations. Don't worry about that. The only thing I expect you to recognize here, and that's why we're talking about it, is they're carboxylic acids. And the prostaglandins, the hallmark here, is always a cyclopentane ring, which is kind of unique there, okay? But again, they're localized hormones that control a lot of things that have to do with pain and fever. And if you inhibit this protein here, you don't make as much of the signaling molecule. You lower the amount of inflammation, pain, and fever. The body tends to overreact upon injury, and if you allow for chronic inflammation, that can lead to a lot of secondary diseases. So controlling pain and controlling inflammation is kind of a tricky thing in the clinic, but the NSAIDs, drugs, are critical for that. Here's the mechanism. I don't expect you to know that. It's a radical process with COX here. It's actually this tyrosine side chain. This is in the protein COX. You see it's green here. Taking off a hydrogen atom from arachidonic acid, which is the starting material, this tetraene carboxylic acid. Yeah, arachidonic acid is also carboxylic acid. So know the basics of that. Don't memorize the structure, but be able to recognize it and see what it is. And then you get this cascade effect. This radical can form the ring here. Oxygen can be incorporated to form this peroxy bicyclic structure. This eventually gets broken open or reduced to the thing there. But the key is the cyclopentane ring. And then the carboxylic acid, some other stuff on there. Don't worry about that. Here's a more recent drug, Celebrex. This was developed Pfizer years ago, and it's now the clinical standard for a lot of chronic pain issues, including arthritis and other pain issues. It's a pyrazole core structure here with a couple aromatic groups. It binds more tightly to COX-2, 2 nanomolar, very potent, and quite potent with COX-1. Now these two different isoforms have different locations in the body. COX-2 is more the peripheral tissues, the limbs and arms and fingers and whatever. COX-1's more in the core of the body. You don't want to inhibit that so much. You want a selective COX-2 inhibitor, and that's what Celebrex here allows us to do. It binds more tightly. Here's a blow up of the structure. There's a lot of secondary interactions. It's the shape and the polarity and hydrogen bonding that allow that to inhibit that and prevent arachidonic acid from coming in. Naproxen's a longer active NSAIDs compound. Our research group came up with a new asymmetric synthesis for it using this catalytic asymmetric methylation of this ester here. We can put that one stereocenter on with high enantioselectivity. selectivity. A couple steps to take things off, but there's the drug there. The S form is the active form that inhibits prostaglandin formation. The R form is actually a liver toxin. So the FDA regulates that Aleve and all these naproxen-based drugs have to be the S form only because of that stereocenter. Yeah, it's increased potency. It's a little greasier, it's longer acting. You only need to take it every 12 hours, as opposed to aspirin, you need to take every couple hours. So you can lower the dosage and get a similar effect. There's a synthesis of Celebrex, yeah, the Pfizer compound. And I point this out, this is the industrial synthesis. They do this on ton scale right here. So here's Frito Craft's acylation. And there's an oxidation of this sulfide to the sulfoxide, and then you brominate right here, and then there's an SN2 reaction right there, and then this reaction right here is an aldol condensation. Maybe we'll revisit that later, a later chapter, to form that. Yeah, that's Vioxx. That one was pulled from the market. This lactone actually has toxicity effect. I'm not, yeah, no, the Celebrex synthesis is not on there. Let's see, maybe it is. No, okay. I'm just showing the Vioxx. It's a little simpler. It has more reactions we've covered. But yeah, again, don't worry about that. But, if we give you this reaction here, you should be able to call that what it is, right? Frito Craft's acylation, okay? Now, these long chain fatty acids. So here's a carboxylic acid that's been ionized with base. And here's our long chain greasy thing here. Now, if you put these in water, you see the polar head piece here in blue can interact with water very well. But this part here, the nonpolar part, forces water to become more organized. Okay, there's no hydrogen bonding here. And this increases the orderliness of this and decreases the entropy of water. And so this hydrophobic effect, and we've talked about that in 351 also, makes these hydrocarbons, these nonpolar hydrocarbons, not soluble in water. But here you have an amphiphilic compound with a polar part and a nonpolar part, okay? So that's what you need to do if you put these in water. Water wants to be hydrogen bound and be able to exchange all the time. But if you put a big greasy fatty acid, carboxylate, and water, yeah, this part's okay up here, hydrogen bonding, but this part down here has problems. So here's how it deals with it. It says, okay, I'm going to stick together in solution here these nonpolar parts, okay? This is the bad interaction that forces water to become more organized. And this is the polar part that can interact with water, okay? It forms these clusters, first of all. Well, eventually it forms these macroscopic multimolecular complexes here. These are called micelles, where the water is completely excluded from the nonpolar part. These bend around and form these ball-shaped structures, where on the blue exterior you have the carboxylates that can interact with water. These micelles can be different sizes and different structures. You have to have at least around millimolar amounts in there. If you have too low amounts of the fatty acid, it will be soluble in water. And if you have too much, it'll begin to precipitate out. And you see that with soap, right? The opaque formations of soap. There's different macromolecular structures here. They're all based on self-assembly or trying to bury the nonpolar part in the interior away from water. Micelles have this type of structure where the entire interior is what, hydrophobic or lipophilic, we can say. And then there are these type of structures that form these bilayer membranes where there's two lipids here, and it has an interior that is also aqueous, okay? This is like the structure of a cell, okay? You have the cell membrane here in between, which has what, a nonpolar area. The interior is hydrophilic, and the exterior is hydrophilic, okay? Those are called liposomes, or little cells. And if you blow up a cross-section of the liposome or have a big structure, you have this lamellar bilayer membrane here, okay? Phospholipids in biology, we need to talk about those. These aren't just fatty acids now. There's actually two nonpolar things per head group. So there's different types of structures that can form these macrostructures. Lecithins and cephalins, these are the standard ones, lecithins in cell membranes, over 90% of them are these glycerate phosphatidylcholine structures. There's phosphate, and here's an ammonium cation. There aren't always all three methyls. Sometimes these are three hydrogens. And then two esters here with long chains. The R groups can be 18 or 16 carbons long, okay? These are the membrane components of most cells. In the central nervous system, nerve tissues in the brain, have a lot of cephalins where it's an ammonium cation, the three hydrogens there. But the rest, the phosphate and the diester is the same. Then we have sphingomyelins, which are kind of specialized lipids in neurons, in nerve cells, where it's not a three-carbon thing here. You see you've got three carbons and oxygen there. I'll show you that later. That comes from glycerol. You don't see that here now. You've got oxygen, nitrogen now. It's an amide bond. And then carbon chain there for sphingomyelin. So that's a different type of structure. But topologically, it's the same type of thing that can form a lipid bilayer membrane. So here's how the structure looks. Oh, there's glycerol getting a phosphate on there, and then a couple of esters, and some other things there. Fat tissues, adipose or triglyceride, acyl triglyceride. Here's the thing: phosphatidylcholines, which are the lipid bilayer membrane materials with a phosphate, and the ammonium with an ethyl. That's called a choline group, diester. And you see here, we can abbreviate it as this little cartoon here. It looks like a little frog. These squiggle lines are the fatty chain esters here. Those want to partition what? Away from water. And then you got the polar head group here, which is a zwitterion, ammonium, and then phosphate, which is ionized, O-. That's going to want to partition to water. And so as these fold up or assemble in water, if you get the critical concentration, these guys form lipid bilayer membranes. There's two pointing toward each other. The interior of a membrane is the nonpolar part. And notice they're held together by non-covalent interactions. It's simply electrostatic interactions where you want to minimize the contact with water and maximize the hydrophobic effect there with the outside on there. So you can compare those to the micelles, which are just these single ball-shaped things from the fatty acids. And this is a basic action of soap. Micelles are the structures that allow greasy material off surfaces to partition in there, and then that grease can be washed away. If you don't have the soap added there, no amount of water will wash that grease off the surface. In order to have the surfactant effect to partition the lipid bilayer, or the micelle, the interior there, allows for the stain, the greasy part, to come in, and then that entire thing can be washed off the surface. Anyway, just know the basics of that. We'll hit some of those other topics later on. So these application things, so don't memorize the structure of naproxen or Celebrex or any of these. Know the basic structures of some of these. Yeah, they're in Chapter 19 because they're carboxylic acids. These have the cyclopentanes, and these are based on benzene. These are all benzoic acids. Naproxen's the naphthalene one there. So yeah, just the basics there and how it relates to the principles. That's what I expect you to know. And I think we've covered everything. Let's see here. Yeah, for the second hour, I believe we're done there. So we'll wish you luck here taking the test later today, and we'll see you on Wednesday. July 8th, we'll be starting what? Chapter 20, moving along. So very good. We'll see you next time. Thank you.